call phi of v. Phi of v. C bar of phi of v. Okay. But for phi of v, I know by Riesz Representation Theorem, phi of v again by Riesz Representation Theorem, this is equal to VW. Okay, VW. So this means this is equal to, if I take this C and throw it inside, it's going to be VCW. Okay, it's going to be VCW. So what does finally you get? You get V phi star of phi is equal to VCW for all V in V. So what does this imply is that phi star of phi is equal to C times W, where the W is this unique vector actually. Okay, W is this, what do you call, unique vector which exists by Riesz Representation Theorem. So this is what is going to be an explicit formula for computing the self-adjoint adjoint operator actually. Okay, the adjoint operator. For all phi in F. This is what the definition is. So in other words, the adjoint of a linear functional is basically this. So take a linear functional by Riesz representation, there exists a W, so its adjoint is what? Phi star of C, so C times the, what do you call, W. Okay, so in other words, the outputs of phi star are the scaled versions of W, so different scaled versions of the W actually. So this is what is going to be one example of, what do you say, the linear functional actually, finding the adjoint but in finite dimensional case. Okay. Another example that we can have from matrices. So let's have another example from matrices, and let's compute its adjoint actually. So let's take V to be the collection of all n by m matrix with Frobenius inner product. In other words, the inner product on AB is equal to the trace of B star A. So this is what the inner product is. Okay, the trace of B star A. So this is called the Frobenius inner product. Okay, Frobenius inner product. So I have a vector space of what do you call, matrices, okay, and the n matrices, and I have this inner product. Under this it becomes an inner product space. You can see this in chapter number 4. We discussed this in class. Okay, and I would like to define, say, a linear transformation that goes from Mn into, what do you call, Mn to Mn. Okay. So let me define, for example, an operator that goes like T of x equal to Ax. Okay. So let's define, what do you call, the linear transformation as the T of x equal to, what do you call, Ax. The question is, what is the adjoint of this? So for calculating this, what you need to do, you need to compute the T of x, okay, and compute its inner product with y. Okay, so this is going to be by definition ax inner product y, and the norm is Frobenius norm. Inner product is Frobenius inner product. Okay, so by definition, this is going to be y star ax. Okay, and its trace actually. So this is the trace of y star ax. Okay, so then this would be equal to the trace of, by using the associativity, I can write this as y star ax. Okay, and hence I can also write this as the trace of a star y star x. Okay, a star y star x. And if you apply again this definition of Frobenius result, so it's going to be x and a star y, a star y. Hence, so what does this show? This shows that the txy is equal to x a star y. So hence the adjoint of such an operator t of x equal to ax is the t star of y equal to, what do you call, a star y. So it is a star y, conjugate of a star y, adjoint of the matrix A times y. So this is really the adjoint. Okay, this is really the adjoint. So we got that. All right. In the final part of the lecture, I would like to prove so-called Bessel's and Parseval identity and the Bessel's inequality. Okay. So in the slide, I would like to prove two very useful identities that are true, and we're gonna use them. We use them at several places actually. So it's like two some of very useful identities. Okay. So the first identity that I would like to prove is the Parseval's identity. Okay. Parseval's identity. So what does this say? So it says that I have a beta that is an orthonormal basis of inner product space V. Orthonormal basis. So it's the orthonormal basis of inner product space V. Okay. There is an obviously it should be finite dimensional. Then here is an interesting thing. The inner product on V and W can be completely determined by taking the dot product of, or the scalar product of, the coordinate vectors of V and the coordinate vectors of W in this basis actually. So what I would like to do is to write more explicitly that this is equal to I equal to 1 to n, okay, V ui times W ui bar, and which is equal to something very interesting, that the inner product can be completely determined through the coordinates of V. So compute the coordinates of v with respect to the basis beta, compute the coordinates of v w with respect to the basis beta, and compute their inner product in Fn, in other words Rn. In other words, just take the simply dot product of v with w in v. So it's a simply, so I know that it's a 1 by n vector, this is 1 by n vector, so simply take their dot product in Fn. So this is going to be really the inner product in v. Is really the situation where it helps us a lot is the theory of the Fourier series, actually, the theory of the generalized Fourier series. So it's a very useful identity, and hence it also have links with the theory of ODs and PDs, actually. Okay. So, and this is true for all v and w in v. Now, how are we going to start? Let's start with the case that since v and w are two vectors and in v, and v is an orthonormal basis, so we proved in the beginning of this lecture that it is really easy to express v in the terms of the orthonormal basis. So what you need to do, you can take ui, and the coefficient of this ui is going to be the inner product of v with ui, and take the sum of it from I equal to 1 to n. So this is what that we proved in the beginning. Shall I write it more clearly? So the v is equal to the sum that goes from I to n. So v inner product ui times ui. Okay, so if you have an orthonormal basis, it is really easy to find what do you call the expression for v in the terms of the orthonormal basis, actually. What would be the description for w? So the w is going to be j equal to, say, n. Take the inner product of w with uj times uj. This is what you're going to get. And now let's compute the inner product, vw. And by the way, this inner product is any inner product. So this is something makes it very interesting, actually, that you take an abstract inner product and you can throw this, project this, express that inner product in the terms of the inner product in Fn. And by Fn I mean Rn or Cn. So Fn, F is R or C. By Fn I mean Rn or Cn. So what is the inner product in Rn? It's simply dot product, actually. It's simply dot product. Okay? Or if it is Cn, so it's going to be a bit different. So x dot y magnitude, or y conjugate, actually. Okay? This is what it is going to be. So let's substitute the values of v and w into the inner product. So it's going to be sum that goes from I equal to 1 to n. Okay? v ui comma sum that goes from j equal to 1 to n, v, not v, but w, uj, uj. This is what that you're going to get. So what I can do, I can pull these sums out by the properties of inner product. It's going to be I equal to 1 to n. Okay? So you're going to have inner product of v, ui, ui. So there is also going to be a sum j equal to 1 to n. And the second component is going to be w, uj, uj. So it's going to be w, uj, uj, and inner product. This is what that you're going to get. Now this is in a scalar. This is a number. I can pull it out of the inner product, and this is also in a scalar. I can pull it out of this inner product. But when I'll put this scalar out of inner product, I need to put it into what we call conjugate. So you're going to have I equal to 1 to n and j equal to 1 to n, you're going to get v ui w uj bar and ui uj. Now ui uj is really what do you call these are really the what do you call orthonormal basis. So ui uj is going to be delta ij. So sum that goes from I equal to 1 to n, j that goes from I equal to 1 to n. So you get VUI times W uj bar, and this is going to be delta ij. Okay. Now in this first sum, this first sum is on j. So which terms of this j will survive? The only terms of j will survive when j is equal to I. And hence the all other will be 0, because delta I is 1 and delta ij when I and j are different is 0. So this sum will become I equal to 1 to n. This sum will go away. So only one term out of this sum will survive, that is VUI, and the term when j is equal to I, in other words W uj magnitude. So this is what that you're going to get. Okay. And what is VUJ? I mean, if you see VUJ by definition of V, if you compute the coordinates of V with respect to the basis B, so the coordinate vector is going to be this. Okay? And if you compute the coordinate vector of W with respect to the basis B, so it's going to be this coordinate vector. So vector in which you have this. So hence you can write this as that this is the inner product or the scalar product of the coordinate vector of V with respect to basis beta and the coordinate vector of W with respect to the basis beta in F and norm. So this is what that you're going to get. What is one and the final thing? So this really completes the proof of so-called Parseval identity. Okay? So the final thing that I would like to prove, so there is a corollary to this Parseval identity, just do it for yourself. The last thing that I would like to prove is the Bessel's inequality. Okay? The last thing that I would like to prove is what do you call the Bessel's inequality. Bessel's inequality. So it's an interesting inequality. Okay. And especially basic inequality is it is also valid in by the way, these both identities are also valid in infinite dimension as well. But we're going to only prove the finite dimensional cases of it. So what is the Bessel's inequality? Okay. So let the same assumptions, let beta u1, u2, un be the orthonormal basis of inner product space V. Inner product space V. I hope this is visible. Of inner product space V. Then for any V in V, we have the following inequality. The inequality says that if you take the sum of I equal to 1 to n of magnitude of V ui square, okay? So in other words, if you compute the sum of the coefficients, because if you see these are, so when you take V and write it in the terms of what do you call this, orthonormal bases, these guys are going to be the coordinates actually in the terms of basis B. So the sum of the square of the coordinates of V in the basis B can be estimated by the norm of V square. Okay? By the norm of V square. So this is what the Bessel's inequality is. So what I'm going to do, I'm going to try to directly do this. I'm going to use some of the identities that we proved in chapter number 4 in our classes physically. I will just quickly recall them. I will not, get into the details of it, and I'll just try to quickly give you the proof of this result. Okay. So I hope this is more visible. Here's a proof. Here's a proof. Let us compute V minus the norm of V minus these guys' squares, or V minus sum I equal to 1 to n V ui square. Obviously we know that this is going to be non-negative actually. Okay, this is going to be non-negative. So what we can do with this I can write this as what? As the inner product V minus sum that goes from I equal to 1 to n V ui, okay, and V minus sum that goes from I equal to 1 to n V ui in the product ui. So this is what that we're going to get actually. So this is like a situation where you have like, okay, u minus v and say w minus z in a product actually. So what you can do then is that you can separate it. So it is going to be uw, uz, vw, vz. Okay? So I can do the same with it actually. So this, I can write this as the inner product vv minus inner product of v with sum that goes from I equal to 1 to n v ui, okay, and minus sum that goes from I equal to 1 to n v ui and ui and v. Okay, so the first term, first with the second, second with the third, and the third with the fourth with the fourth. So the final term that you're going to have is going to be the inner product of what? Of the sum I equal to 1 to n v ui square times inner product of I equal to 1 to n v ui inner product. So this is what that you're going to get actually. Okay. So if you simplify it a bit more, okay. So this is going to be what? So this is going to be the norm of v square. Recall the property uv is equal to vu bar. Okay. So if you have, so this is one of the basic consequences of the definition of the inner product. So if you take uv and add say vu into it, okay, then this is same as that you take uv and add uv conjugate into it. And we know that if I add a complex number into its conjugate, it's going to give me, what do you call, the 2 times of the real part of it actually. So in other words, if you add z to z bar, you're going to get 2 times of the real part of the z. So this means that this would be equal to 2 times of the real part of uv. Okay, so this is what that you're going to get. Finally, so for the first term you have this, and if you see, so this is like v and this term and v. So if you add these both terms and do this analysis, then this would be equal to minus 2 times of the real part of what do you say, v and sum I equal to 1 to n, okay, v ui and ui, okay, this is what that you're going to get. And the last term is obviously going to be the square, because in the inner product the both vectors are same, so this would be equal to plus the norm of I equal to 1 to n and v ui and ui square. Okay, so this is what that you're going to get. By the way, for this we kind of had what do you call the generalization of Pythagorean theorem actually. So this is really one of the first few things that we proved in today's lecture was that this guy basically equal to what do you call this factor actually. Okay, so just keep your books open and have a look. So you're going to get what that this is equal to 2 times of the real part of v sum I equal to 1 to n. Okay, if you wish, you can pull this sum out. You're going to have the sum of 2 times of the real part of the sum I equal to 1 to n and v in the product v with ui. So I just pulled this sum out. Okay, plus this guy would be equal to what? The sum I equal to 1 to n of the squares of the magnitude v ui square. Okay, so this was one of the first thing that we proved in today's lecture. Okay, so we are almost there. I mean, if you think that we are almost there, okay, so the only thing is to just think about this middle term actually. So what should be done? So I can do what? I can do another thing. I can pull this number out. Okay, I can pull this number out of the inner product. Okay, so what are you going to get then? So shall I write it? So let's keep the first term as it is, minus 2 times of the real part. So if you pull this number out of the inner product and this number is in the second component of the inner product, when you pull it out, you have to put the conjugate actually. So you're going to get a real part of the sum that goes from I equal to 1 to n and the conjugate of v ui bar times v ui